my best to keep you awake, and I'll speak of dynamics of shear bands. So my talk goes back to a few years ago when I was preparing a simple model for shear band in a sample. We see here a sample pulled in tension, and we see two shear bands appearing. So my intention was to simplify this situation, and my first thought was, why do not we put only one shear band instead than two? And then I said, we can make it this easier because this material and that material will be elastic. Why not to idealize both as elastic rods and the shear band as a slider? A slider is a device which allows free sliding without any friction. When I sketched this simple structure, I immediately realized something. I realized that that structure has a tensile buckling. So it buckles in tension, which is something unusual because engineers are used to associate buckling to compression. And so what I did was to sit down and write the equations. The equations are based on the Euler-Elastica nonlinear differential equation. Then we have the equilibrium of the slider, this one. We have the fact that the force that transmitted to the slider has to remain orthogonal to it, and we have the kinematic compatibility condition across the slider. So we have two elastic rods connected through a slider. We did all this math. The solution came in a closed form, and in fact it can be proved that this from the bifurcation point of view is a standard Sturm-Liouville problem. It admits tensile buckling and then infinite buckling in compression. We also did the experiments about this because this was something curious. So we decided to pull two elastic rods in tension. I don't know why the movie doesn't work. Yeah, this is the buckling, elastic rod, the slider is very long to allow large deformation. We see here a photograph during one test. We see the elastic rod, the other elastic rod, the slider. So this buckling in tension is a reality, both from analytical point of view, from theoretical point of view, and from experimental point of view. When I derived this, I realized something. Imagine that now these two materials are neo-Hookean, and imagine we use a sliding interface with the condition that all people usually implement for this problem. So null incremental nominal shearing tractions across the interface, continuity of incremental nominal normal traction, and continuity of the normal incremental displacement. If we introduce these conditions in this interface, and this is neo-Hookean subject to tension, there is the so-called Hill's exclusion condition for bifurcation, which says that bifurcations are excluded for this problem. But we know that bifurcations here are reality. And then I started to think to this. More in general, if we use a so-called spring interface, a spring interface is a sort of generalization of a sliding interface because we have the continuity of incremental nominal tractions, normal and tangential. We have a linear relationship between incremental tractions and jump in the incremental displacement. We allow the possibility of a jump. But what happens is that in the limit when the stiffness of the interface goes to zero, we recover the model of sliding interface for which bifurcation is excluded. If we apply the Hill's exclusion condition for bifurcation to these conditions, again we find no bifurcation. And this contradicts both the theoretical results and the experiments. So I started to think that something was missing in this condition, incremental conditions. And so I thought how to formulate slip when solids in contact suffer large displacements. And this is the research team of people who worked with me on this topic. Diana is a PhD student, Domenico is an associate professor, as Andrea Picoros, Stupkiewicz from IPPT Warsaw is a professor, and Nicola Bourdignon is a PhD student. this is the idea, is to introduce a simple model for a slip interface connecting two solids which suffer large displacements. So we assume lack of friction, and we assume that the interface is bilateral. It means that it cannot detach. That's a strong simplification. Why to analyze this problem? I am an engineer, and I have always some, let's say, ball breaker who asks me why I'm studying something. I have always to motivate what I'm doing, and so I struggle myself to find a motivation for this problem. For me, it's only a cultural motivation, but I guess that at the contact between lens and cornea, we have the contact between two soft solids. Also during aquaplaning tires, articular cartilage are examples of slipping interfaces connecting soft solids. And then I also went in my lab and I did a simple experiment to show that these tensile bifurcations exist when we consider highly deformable materials. So we see here this T-shaped element, which is rubber and is connected with a suction cup. This surface is oiled. We see a testing machine, so we pull the suction cup in tension, and we see this tensile buckling where the suction cup slips on this horizontal element. So this is something which exists. So how to treat this problem? The basic ingredient is to realize that two different points belonging to the upper and the lower part of this body may become a single point in the deformed configuration. So this condition is expressed by the equality of the two deformations governing the displacement of this point and that point. So this is the basic condition that I have to use, and then there is some math which I would like to skip because it's too late for that. It's somehow standard but a bit complicated. So we'll get the kinematics and the stress rates which look like that. And if we concentrate on the specific case of planar interface, we get these conditions. So the first condition is the continuity of the normal component of the incremental displacement, 100% standard. The second condition is the equality of the two incremental shear components. Again, the second condition is completely standard. What is not standard are the other two conditions. The incremental shear along the interface is not zero, as usually people assume, but it's a function of the normal component of Cauchy stress. So this is the sliding interface. We have the normal component of Cauchy stress T and N. We see that this component enters in this equation. Second, the last equation is also non-standard because people usually take the difference between the normal component of incremental traction to be zero, but here again they are a function of the Cauchy stress orthogonal to the interface. So we recover the usual conditions only if the component of the tension orthogonal to the interface is zero. Only in that specific case. Otherwise these conditions are different. So usually people take alpha equal to 0, and we see that the correct solution is not that, but is alpha equal 1. Now, if we analyze the bifurcations problems I have mentioned before, for instance, two elastic half spaces in contact with a sliding interface and pulled in tension, we see that the correct condition and the wrong condition have differences in this area. In that area. So the difference is small, but the consequence is important because the fact that there is this blue area there means that here we have tensile bifurcation, here with the wrong condition we have not. So the wrong condition prevents bifurcation in tension. This remains more or less the same if we analyze more complicated problems. For instance, we have a layer on a half space and they are separated by this sliding interface, and we have now a tensile orthogonal stress, And again we see that with the correct condition the bifurcation diagram is completely different. Completely different. Again, if we consider two layers, pulled in tension with a slipping interface, the correct condition and the mistaken condition give completely different answers. The very last treat we did this was done numerically because we weren't able to solve it analytically, so we have these two Neo-Hookean layers separated by a sliding interface. We pull them in tension and we see that we find bifurcation, and actually the solution converges towards the solution of the two elastic rods when these layers become thinner and stiffer, of course. So at this stage we believe that the correct interface condition for sliding is that with alpha equal 1. Now we can analyze more complicated problems. For instance, we may look to coated cylinders, and we can assume that the coating and the cylinder, the elastic cylinder, are separated by a sliding interface, and again we find completely different results with the wrong and the correct condition. But eventually the interest in my talk is in shear bands. So shear bands are a sort of sliding interfaces, but actually they differ because the shear bands are assumed to follow these rules, and these rules are not corresponding to the slip conditions I have shown before, but let's say they look like the wrong conditions. And these are the conditions which occur at loss of ellipticity in the incremental response of an elastic solid. So now we stay with these conditions, and we see what happens when we have a shear band embedded in an infinite medium, and a wave is arriving and is impinging this shear band. That is our interest because shear bands exist in materials. They are precursor to failure, and we are interested to know what happens when a material containing one starts vibrating. We cannot do experiments. Experiments like this are impossible, so it's better to have an analytical model. So for the material of the infinite body, we use incremental elasticity, the so-called J2 deformation theory of plasticity. It's a nonlinear elastic law which mimics the behavior of a plastic material. These are the constitutive equations. The increment of the first Piola-Kirchhoff stress, P dot is a Lagrange multiplier because the material is incompressible, and we see that the elastic tensor contains the state of stress, sigma and P. P is the average stress and sigma is the deviatoric stress. So these are the constitutive equations. We have to analyze this problem. To do this, we need the infinite body time harmonic ring function, which actually we found years ago together with John Willis. It looks like this. It's let's say it can be used directly, and we need also the boundary integral equations to treat this problem. This can be obtained from the Bethe identity generalized to this context. We are in an incremental elasticity context, but the Bethe identity looks almost the usual one, and based on this condition we derive the boundary integral equation for the scattered wave field. The material is incompressible, so we need also a boundary integral equation on the increment of the mean stress, which is the analogous, the generalization of an equation given by Ladizhenskaya many years ago. So it looks like this, and we found this some almost 20 years ago together with Domenico. We have to put all this together in a numerical scheme. I will skip details because, by the way, I'm not an expert in numerics. Domenico is one, and he helped me with this. And eventually I can show you results. For the J2 deformation theory of plasticity, we have an inclined shear band like that. In this case, we have a horizontal wave impinging, and we have plotted the stress intensity factor versus the frequency of the signal. Here the wave is horizontal, here the wave is aligned parallel with the shear band, here the wave is vertical, and here is orthogonal to the shear band. One interesting thing of these curves is these peaks. The peaks corresponds to resonance. The body is infinite, so there is a damping due to the fact that the body is infinite, so we don't find the graphs blowing up to infinite, but they have peaks, and the peaks are the effect of resonance. Now, this is the scattered field, and this is the total field. For a shear band, we see it there. We see it there. So we see there are horizontal wave arriving like this, and the presence of these shear bands produces a scattered field, which is visible here, all these very thin waves. So the fact that we have that disturbance produces all these waves which extend to infinite, because we are very close to the border of loss of ellipticity, and so the material, the local effects do not decay, they propagate up to infinite. So this is the situation with one shear band. We can see what is the influence of the state of stress, because this is an incremental solution superimposed to a given state of stress. So when the stress is low, the perturbation induced by the shear band is small, and when the stress is high, is very close to the border of ellipticity, the perturbation grows up to infinite, and this fine texture of very thin waves. By the way, there is something interesting that we see, that there is also a shadow zone forming ahead of the shear band, which can be visualized with these techniques. This is a detail. Another thing that we can do is to analyze the interactions between shear bands. We can take two parallel, two aligned, and two convergent. And again, we consider a wave propagating in this material. So this is the situation with two parallel shear bands, and we play with the distance here. We may see that depending on the distance and depending on the frequency, we may have a focusing effect between the two shear bands like that, so the signal grows inside the two, or we may have a sort of shielding effect. The two shear bands prevent the material inside there to be deformed. So in the first case, a third shear band will form immediately. In the second case, nothing will happen in between. And this is the case of two of the stress intensity factors for two shear bands. The wave is orthogonal, and here the wave is parallel. Again, we see all these peaks, which is the interesting part of these graphs. And eventually, the case of the two convergent shear bands produces a very complicated pattern of waves. This is the scattered field, and this is the total field. We may see that there is this texture of inclined waves. And with this very last image, I would like to thank you for your patience. We are at the very end of the day, and thank you. Problem, how to solve all this with the Wiener Hopf?
Okay. One question, please. You know, you assume in theoretical formulation and made in the experiment you shown in the beginning that this normal to the axis cross section remains at the same plane. Remains at the same plane. Yeah? No normal break.
Opening. No, it's not a fracture. Yeah.
So in this case, it's clearly that this is buckling and so on. But could you show a free beam under tension with such an effect?
Opening fracture.
Yeah. Not to prevent opening.
Yeah, we have done this with a spring interface.
I'm very doubt that it is good possible.
I tell you.
Wrong.
No. I tell you the story. So what we have done as an answer to your question is the following. We have taken two blocks of elastic materials. Elastic, yes. And we have put inside here a spring interface both longitudinal and tangential. Okay, so a spring interface in this direction and in the shear direction. Okay. Now what we have done is to keep, imagine this stiffness is K horizontal and this stiffness is K vertical. Okay?
Okay, if you make KV too large comparing with the KH, you obtain this.
Exactly.
But is it in nature?
Well, nature.
You know.
Yeah, since
in nature.
this is nature, for instance.
No springs, no saturation.
This is nature.
Yeah, but you made this experiment preventing opening.
Yeah.
But if you have a free beam, you have no such restriction.
Well, you mean a free beam with a hole or with a crack?
This, a device without this making no opening. Okay.
I can give example of.
No, but yeah.
Just free beam. Okay.
Yeah, there will be a
take free beam on
yes.
the machine and then under tension.
Yeah.
I never saw such a
Sure, because of course you should invent something which resemble that condition. So one example would be, imagine we have an elastic beam made of a matrix. Okay, let me answer. Made of a matrix material with stiff fibers. It cracks like this, but the crack is prevented to open because of the fibers, and then it does the same thing.
Okay, it is a special case, I don't
Yeah.
know. I would like to see the homogeneous material, usual beam, which is usually tested in the tension.
No, the usual beam doesn't do this because this is
a very special.
Yeah, the unusual beam of homogeneous material doesn't do like that.
So
Yes.
if we make experiment as you shown, we have this. I agree. But if not, it is under question.
You can see this in biological systems. Dislocated shoulder is.
Yeah. Not only shoulders, fingers. I have been told by a medical doctor, but I'm not one, so I don't know, that if a finger is pulled, then there is the contact between the bones. It's a sort of saddle surface that in one direction it goes in compression, in the tensile direction it dislocates before breaking. So I have been told.
This is under pressure, by the way. You put in under tension.
Tension.
Where is the pressure?
No, I mean, in a finger you can press it,
Yeah.
or you can pull it. A finger can be pressed.
What do you say? Press and in tension? Yeah.
No, I mean, a finger can be pulled.
Yeah.
For instance, one guy who climbs a tree, the fingers are in tension. So I have been told by a medical doctor that in tension, the bones doesn't break, but
Don't
dislocate.
show your finger to a doctor.
But I can do another example on something like this.
If a doctor has such a device,
I can do an example on this. I can do an example on this situation. If you want to play with something. Question: can you imagine an elastic structure, simple one, 1 degree of freedom, which has 2 bucklings with 1 degree of freedom? Usually my colleagues say no. They say no, I can't figure out it. But the answer, as in many of these cases, is not so complicated and is related to this the discussion. So let's do like that. Imagine we have a rigid bar, and this rigid bar has a roller here, and imagine it is constrained to move. This pin is constrained to move along a circular profile. So we put here some elasticity, and this system has 1 degree of freedom. Okay? It has only one bifurcation in compression. When we compress it, it goes like this.
yeah.
Okay. Now let's do another example. We consider the same structure. exactly the same structure, but this time instead of having this constraint, we put the other way around. Now it has a 1 degree of freedom and has a tensile buckling because it does like that. Okay? Now if we combine together these two structures, we get something like this.
Yeah, but where is such a core?
And now this structure has a bifurcation in compression and a bifurcation in tension. 1 degree of freedom, 2 bifurcations. The reason is because the Hessian of the total potential energy is discontinuous.
There one condition that these curves are rigid. Where such a curve in
Bones are rigid.
Bone.
The junction, the thing I was explaining before with the finger is exactly this. The finger is made in a way that if we compress in one direction, it has a bifurcation because the junction is like a saddle. So in one direction it bifurcates in one way, in tension in another way. It's bone dislocation.
Okay. Thank you very much.
My pleasure.
Can I ask another question? Based on your video, which included the experiment, this bifurcation and the tension is a dynamic process. Well, it produces a sound, so it must be a dynamic process. So you store some energy, then you release this energy, and then it generates waves. And these are fluctual waves and pressure waves. Is there any way to estimate how this energy is shared between the pressure waves and shear waves as a result of this?
The reason why it's not, we hear the noise, and the reason why there is energy release is due to the fact that the post-critical behavior of that structure is unstable. So this is P and this is delta. So the structure is made like this. There is the slider here, and there is a clamp. This is a moving clamp. So when we pull it in tension, P, it has a bifurcation where it takes this shape, more or less. And if we call this displacement delta, the P delta diagram is something like this. This is the fundamental path. We assume, as usually in these problems, inextensibility, and then there is a critical load, and there is a post-critical behavior like this. So in the real experiment, what happens is that the load in a real experiment, we are never in a perfect condition like this. So the experiment goes like that, and then here we have a fall of the load and the production of the sound and the waves. So if the problem is to estimate how this wave propagate in the structure, this can be done for sure numerically, but maybe we could also try to invent something more intelligent and brute computations.
I didn't ask about modeling the waves. The question is sort of more basic. Can we say anything about how the energy is shared between the pressure and shear waves when you initiate this?
I can't tell you immediately. One has to do calculation to see this. For sure, in a road model like this, since the axial deformation, as you know, the axial stiffness is very high, and the flexural stiffness, on the other hand, is very low. So, of course, one has to play with this sort of situation.
So, in simple terms, can we say that the tensile waves are dominant in this case? So the contribution from flexural.
I would not feel myself sure. I cannot tell you.
Okay. Thank you.
First of all, thank you very much for this. Actually, as a organizer, I would like to say something. As you can see, I try to invite not only people who are really speaking about linear flow, but who has in their presentation wording like dispersion diagram, crack, transmission condition, And something what is absolutely interesting in terms of phenomena, and observing some talks where people speaking about again standard Wiener-Hope with some standard situation, trying to guess where we can use it. I suggest to think about very unstandard situation. What is very interesting features where can we really use it, because we are not everyone meeting this in our conferences, and then in terms of geometry, in terms of conditions and all on, it's very quite in this region where we can use Wiener-Hope. Okay, so this is only comment. I'm not asking anything. Any more questions?
So you had this example towards the end of two parallel shear bands, right? And I think you said, depending on frequency and the distance between the two, you have different patterns, right? So the scatter field, including some resonance type effect, right? When you have this kind of bouncing thing between.
Yes.
What is the result of simulation, right?
Yeah.
There must be a simple explanation, right, in terms of this resonance, right? Is a kind
Yes.
of almost
Yes. When you have
quasi mode, right, which you can construct analytically, right, in between two parallel shear bands, but we do need to know how to model this reflection coefficients, right?
Yes. Yes, I didn't follow you exactly, but two shear bands, in a sense, introduce a structure in this infinite body. So resonance is produced by the fact that there are at least two characteristic lengths. One is the length of the shear band, and the other is the distance. So playing with these dimensions and playing with the wave frequency, of course we can induce situations where, I mean, the resonance is important because in that situation the shear band will grow fast, they will touch, they will merge, they will move. It would be beautiful to be able to do experiments, but here experiments are almost mission impossible, because how can we imagine to monitor a shear band? Usually shear bands form inside the bodies. So how can we imagine to monitor something which is inside the body, very small, during a dynamics? It's very difficult, but at least here we can have an idea what is going on and what are the conditions why these shear bands try to grow, to start at a point or another point, so on. One thing which I can say, that this boundary integral equation is very accurate. We have developed ourselves, and actually we used also some suggestion from Sasha, who told us how to manage with these singular equations. And it's very precise. We cannot obtain the same precision with the standard finite elements. We cannot, but.
Shall we thank our last speaker and post this session?